Okay, so we're going to be talking today about the next type of goal that we might have when we're trying to optimize our decisions, which is minimizing the expected loss. So when does that come up? So, for example, let's return to the case of the cancer diagnosis. Um, the types of errors you're going to make there aren't going to all be equal. So it's going to cost a lot more if you have a false negative. So if you tell someone that they don't have cancer when they do, because that person might get a lot more sick, they might even die um, prematurely, than if they don't have cancer and you tell them that they do. So in that case, the person will probably be quite distressed, and you might have to do additional examination. So it's going to cost some grief and some money, but it won't be quite as bad as telling someone they don't have cancer when they do. So in those situations, it's not just about minimizing your misclassification rate, which would value both of those types of errors equally, but some misclassifications are more expensive than others. So um, you want to avoid making those if you can. So that's what minimizing in this expected loss is all about. So, and we kind of capture our notion of how expensive different kinds of mistakes are with a loss function or a cost function equivalently. Or if you're trying to maximize instead of minimize, well, you would call it a utility function. So, the benefits you would get from making decisions. And the way when you have kind of discrete classes of whether someone has cancer or not, we can deal with that loss function becomes a matrix. So a matrix, L of kj, where k is going to be the true class and j is going to be the class that you're going to assign. So here, for example, here's one example of what that might look like. So here we've got the true classes. On the left, we've got cancer versus normal, and then you've got the assigned classes. And now you have four kinds of decisions. One of them is a true positive, so the person does have cancer and you've detected the cancer, so there's no loss in terms of your algorithm there. There's also a true negative, so they don't have cancer and you've also detected that as no cancer, so that's good. Now, one of the cases is the false positive. So they don't have cancer, so they're normal, but you said that they do. And so again, that is going to cost something. So we'll assign it a cost of 1. But it won't be nearly as bad as if they actually do have cancer and you say that they don't. So that's a false negative. And in this particular example, the false negative is going to be much more costly. We won't really want to avoid those. And if we make some false positives, like that's okay. And this isn't a property of false negatives and false positives. Different problems might have a different assignment and a different kind of balance between the two. Um, so, so this is our matrix capturing the losses for this two-category case. And so the question is, well, how do we make decisions in this setting? So obviously, if we knew the true category, that someone, that a particular person or a data point came from, well, then of course the rule would be to assign them to that category. But the situation we're in is that we actually don't know what the true category is. And we've quantified our uncertainty with this probability P of x. P of x, C of k, which says the probability of a data point coming from a particular class. So instead of just assigning to the class where if we're when we're fully certain, when we're uncertain about the class, then we have to minimize not the loss itself, but the expected loss. And that's the expression for it here. And it has a few pieces that we should go over. So here's our expected loss. And the way we compute it is, well, first we loop over the possible true classes. So we're going to loop over cancer and no cancer. And then we'll also have an inner loop over the assigned class. And now we're going to integrate over our observations, but selecting only the data points that are being assigned to a particular class J. So that's what this Rj integrating over Rj does. And then we contribute the loss. So we add up the loss for having a true class K, but assigning it to J. And finally, we just weight it by the probability of that data point. So the probability of that particular data point being in the class K. So this class K is the thing we're looping. We're looping over the true classes, and then we loop over our assignments, our given assignments. So as indicated by this index J and by these regions of the input space. And now we just weight the loss by the probability of, by the density of points according to the, the class that they're actually from. So now he just next states, well, so now the game is of course picking these assignments to the classes. So essentially setting up these regions. So how do we do that? And he says, well, the thing we should minimize over J, over the assigned class, is this quantity. So what is this quantity? So this quantity is the sum over the true classes of the loss for each one of those true classes, given that we've assigned to the class J. So this is that we've assigned to class J, the true class is K, and just weighted by the probability of data points being from that true class. And so for every single data point, and we can do this independently, we want to assign it to the class J that minimizes this quantity. You can think of this as the expected loss for that data point given an assignment J. And I thought it'd be useful to maybe go over this in a slightly different way, just to kind of maybe it might make a bit more sense. I mean, his notation here is correct, of course, but I find it a little bit more useful to think about it slightly differently. So let's try going through that computation and seeing what we arrive at. Okay, so let's make sure you can see everything. Okay, very good. Okay, so what are we doing? So we've got our expected loss. And what was that? Well, that was a sum over the true classes, so K, and then a sum over the assigned classes, J, of this integral that's going to now pick out our assignments. So pick out the region J, that's the points that are in that have been assigned to this particular region. And now we're just going to add up the loss. So this is the loss for data coming from a true class K being put in a class J, and then weighted by the probability of data points being from that true class. So that's exactly the expression that he has above. So I like actually to write this slightly differently. So instead of kind of picking out these regions, I like to be able to integrate over the whole space and then have a function, kind of this rule that's going to assign points to regions, to classes. So our aim is, we're going to be looking for a rule R that maps X to one of these numbers 1 to n. So that's going to be the J. So let's just rewrite our expected loss in a slightly different way. So we'll write it as, again, the sum on K and a sum on J. So this is a true class again, the assigned class. And now I'm going to integrate over all of space. So there's not going to be an RJ down there. And I'm going to have this little indicator function that detects when the rule has assigned a data point to a particular class. So I'm just going to use kind of programming notation, logical indexing. So this function is going to be 1. So this function is going to be 1 when Rx equals J, 0 otherwise. I think it's pretty self-explanatory. And then everything else before. So now LKJ, so this is the loss again of assigning to class J when the real class is K, and then weighting everything by the probability of those data points. Okay, so now what we're going to do is, just to really emphasize that we can do this minimization at every single point, we're going to move the sums inside the integral. So I'm just going to say, well, this is actually the same as a sum over all of space of this K, so summing over the true classes, summing over the assigned classes of our indicator, and then again just the rest is the same, times P of X CK. So now the point of this is now, our job is now going to be to minimize this thing over, we can do this pointwise now. So we can actually minimize, we want to minimize E of L. So let's actually write it out. So we want to minimize, can you see this? No, maybe too far to the left. Minimize over, R of x, this, this whole integral dx, da 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 da. So that's kind of what we wanted to do. But now, because we can, we have these functions that are kind of independent at every single point x, we can actually minimize, perform the minimization pointwise. So I can actually minimize this at every single point. So our job will then be to, so it goes to, minimize over Rx, with some abusive notation now, this thing. So, we're just going to take that integrand and just look at every single point and minimize over R of x at that point. So again, it's another way of saying that is we're going to come up, and the rule is just going to operate independently at every single data point, and we can set the rule to be whatever it needs to be for each data point. Okay, so now what is this thing that we're looking at? What is this function? Well, the first thing to do is we can just look at what this does, right? So let's do this first. So what does that do? So this sum over j of r, of r of x being equal to j, it will actually just pick out the j that equals r of x, right? Because this thing is going to be 0 unless j equals r of x. So we can actually replace this. This is just going to be L, k stays whatever it is, and I'll just put a comma, r of x. Okay, so that sum is kind of collapsed into just a single value, because if r of x doesn't equal to j, well, lkj doesn't contribute. So it becomes 0, and that drops out. So now we want to minimize, we want to find, this assignment, sum on k of p of x ck. And this, if we just, change labels to, if we just change our labels to j, this is the same as what the expression that he had. So we're just performing this minimization pointwise at every single point, for every single x. And these indicator functions kind of pick out the parts, the assignments that we make, and that assignment then picks out a particular part of that loss matrix, and then we just we sum over it. And again, what is this thing that we are minimizing over j? Well, this is the expected loss. So there's the lk of j of making the assignment of a data point to j over all, all the true, all of its true assignments. So you're saying, well, I'm going to assign this thing to j, but it could have come from any of these other k's, and this probability distribution captures the probability of that happening, and the loss captures the, the loss that you incur when that's the case. So I think that's hopefully that maybe that gave them a slightly different angle on it. Maybe it helped make it clearer, hopefully. And I thought, okay, let's look at a couple of examples of just what this would look like. So in the previous section, we talked about the misclassification rate, and so the first thing I want to show you is that corresponds to a particular loss. So you can imagine, so let's consider a loss. So let's consider a loss matrix that looks like this. 0, so it's zeros on the diagonals as before, saying that if you assign things correctly, it's you don't incur loss. But then everywhere else it's 1. It doesn't have to be 1, but it just has to be the same value. We'll just assume it's 1. So in this setting, any misclassification is going to be weighted equally. So it's, we have the flexibility of weighting them differently, but we can also just weight them all the same. And what I want to show you is that this will then give us the same answer of what to do, gives us the same rule as that we found the last time when we were just looking at minimizing the misclassification rate. So now, if this is the case, let's just look at one of these terms. So let's say we said the sum on k, lkj, p of x ck. So what does this look like? Well, you can see that it's going to be equal to 1 for all the j's that don't equal to k, and then 0 when j equals to k. So this is going to be the same as sum over k does not equal to j of p of x ck. So in that particular setting, and what is this? Well, this is the sum. You've assigned a point to j, but the true class, the probability is the true class is not j, it's something else. So this is exactly this is the misclassification rate. So this is misclassification rate of assigning x to j. So in that setting, then you pick the j that minimizes. So minimizing this over j is exactly the same as minimizing the misclassification rate. So that's just to say that this loss matrix framework encapsulates and is more general than just capturing the misclassification rate, and it can do that as well. So this is capturing misclassification rate is a special case of for these loss functions. Another interesting example I thought we should look at is the case when we're very certain. So when you actually when you know what the true class is. Well, what should you do? Seems like the obvious answer is assign x to that class, and we'll just see how that comes out. And we'll do that actually using a remark that he makes at the end of the chapter, which is that we can think about this in terms of posterior probability. So we've got a joint probability of x coming from a class ck, but we can actually just use I guess it's the product rule to write it slightly differently. So let me just make a break here. So this is let's go to a new. So the case of perfect information. I'm just going to call it that. I've just made this up. Okay. So first, and actually before we talk about perfect information, let's discuss what he wanted to say. So again, remember our rule is to minimize, so r of x is going to equal argmin, I think this is maybe too much, of over j, I think you'll know what I mean, of lkj, sum on k, lkj, so the losses that we're going to incur, right, weighted by the probability of the data points. Okay, so the first thing is we can just write this as use the product rule, ck, right? So this is the prior probability of that data point regardless of what class it came from, and then the posterior probability of the true class given the data point. So now we can then notice that where we care about j and we care about k, this px is like a constant. We can just move it out. So we can just say this is the same as arg min. This minimum over j is not going to matter. It's not going to change if we multiply it by a constant like p of x. So let's just say this is going to be the same as because all of these terms, all of the for every single different j that we consider, it'll always be getting multiplied by the same p of x. So we can just drop the p of x and just work instead in terms of these posterior probabilities. So that's what he's going to talk about. That's what he mentions at the end of the chapter. That the rule is the same. You assign j to the class which has the lowest expected loss under the posterior probability of the true class. So now, what does perfect information amount to? Well, that amounts to p of ck of x being equal to, let's say, 1 if k equals, I don't know, let's just call it r, and 0 otherwise. So that's kind of like someone has told you that you know that x comes from, once you see x, you know exactly which class it comes from. Okay, so what does that look like when we actually put it through this machinery? So let's just do that. So now we say, well, arg min of j, sum on k of the loss. And now P of ck of x, I'm going to just write this as, let's say, k equals r. Okay, so now k equals r. So what does that do to the sum? Well, what it does is pick out the rth element, the situation when k equals r, because when k doesn't equal to r, this has become 0, so it doesn't contribute anything. So what this amounts to is arg min over j. Maybe I should actually even spell it out. It should be clear, but let's just show you what I mean. So let's say for we've got L0j does 0 equal r plus L1j times 1 equals r dot plus L rj r equals r plus dot. And now you can see that, well, this is going to go to 0, this is going to go to 0, and so the only thing that's going to survive is this term. So what we end up with is just arg min over j. So it's going to be this whole sum is going to be the arg min over j of whatever this whole sum amounts to, which is just L rj. Okay, but now we know for the loss matrices that we're talking about, their diagonals are 0 and everywhere else is greater than 0. It could be different, but most reasonable loss matrices will have this property. And so in that case, the minimum value of j over j of LRJ, so that's going to equal, that minimum value is going to happen when j is equal to r, so the arg min is going to equal r. So the rule, when you have this perfect knowledge, is to assign the data point to the class you know it's from. So going back to the cancer example, if you know the person has cancer, we'll then assign them to the cancer example. And if you know that they don't, we'll then assign them to that case. So it's very common sense, but I'm just trying to show you how it also arises from these rules that we have. So assigning the class that has the lowest expected loss, where the expectation is computed either using the joint probability or equivalent using the posterior probability of the true class given the data point. So I hope that was interesting. I think the chapter concludes with the section concludes with just what we talked about, that we can actually equivalently minimize the expected loss using the posterior probability. And then he says, well, this is clearly trivial to do once we know the posterior class probability. So so usually this is the hard bit, figuring this out. And once you have that, and you've arrived with a loss function, otherwise you can't do decision theory, then you just do this, you form these kind of linear, these just weighted sums, and you minimize that. So it's a really easy thing to do once you've got these posterior probabilities. Very good. So I think that's all I want to talk about in this section. And next time we'll have a very brief section on something called the reject option. And I'll see you then.